Hey guys, today we're going to take calorimetry one step further and we're going to look at the calorimetry of a chemical reaction. This means we're connecting the change in potential energy that occurs during a reaction, which we have already talked about as the change in enthalpy, or delta H, to the Q, which we just discussed in the last video. So let's go ahead and use a reaction to discuss what's going on in this process and be able to quantitatively assess how much energy is transferred into the system or into the surrounding. So let's start by reviewing what we've already learned. First thing you need to remember is that any chemical reaction is going to experience changes in potential energy. Potential energy is inherent to the chemical bonds and the chemicals that exist and thereby are reacting. If the chemical energy in the form of potential energy is going to decrease over the course of the reaction, that energy is released in the form of an exothermic process. That exothermic process, that energy which is released, all right, is the focus of what we're looking at today. Secondarily, if we are going to have a chemical process where we are going to increase the enthalpy from reactants to products, that's an endothermic process, and the energy that's going into that system is going to be absorbed and is going to be the focus of our video today. Now, in the last video, we discussed Q. Q, remember, represents heat and is quantitatively measured using the equation mc delta T, where mc delta T represents the energy change of our surroundings. So today, we're going to use the same mc delta T equation in order to represent a change in kinetic energy that's coming out of a change in the potential energy of a system. The reaction we're going to use in this process to be able to kind of show how the change in enthalpy can cause a change in the kinetic energy is going to be the neutralization reaction between sodium hydroxide and hydrochloric acid. Now, for simplicity's sake, we're going to use aqueous sodium hydroxide reacting with aqueous hydrochloric acid, and this is going to produce sodium chloride, which is aqueous, and water, which is a liquid. So here's that practice problem. I'm taking aqueous hydrochloric acid and aqueous sodium hydroxide, and in doing so, I'm producing water and sodium chloride, which is also aqueous. Now, if we think from a purely conceptual manner here in terms of bonds breaking and forming, when it's already aqueous sodium hydroxide and hydrochloric acid, those have already separated apart. So it's H plus and Cl minus, and Na plus and OH minus. So those have already separated into the solution. So there's actually not going to be an energetic aspect of that. Water, though, is going to form as a part of this process. Now, those are covalent bonds that are forming. That's actually a bond that's forming in this process. However, sodium chloride, it's not actually going to be there. So in the end, if I were to do a net ionic equation for this process, it would be H plus OH minus reacts to yield H2O, and that's it. In other words, we have a synthesis of water going on in this neutralization process. We'd expect, because more bonds are formed and no bonds essentially are broken in this process, we'd expect this to be overall an exothermic process, energy released. Remember, energy is released through the formation of bonds. So we've got a setup here. Now, there are a couple of assumptions that we're going to go ahead and make as we go through this process, but the first thing we're going to do is set up the equation that we're going to use here. We see a change in temperature. Now, the change in temperature is that of the solution. And this is kind of weird because the solution is not like water like it was in the last video. The solution in this case is going to be somewhere a mixture of this HCl and NaOH, because they were already aqueous. They were already in water. So there are a couple of assumptions we make. The first assumption we make is that we assume any solution that is not pure water is going to have the same properties of water in terms of specific heat and density. So we're going to assume the density of this solution is 1 gram per milliliter, and we're going to assume that the specific heat of the solution is 4.18 joules per gram degree Celsius, which is the same as that of water. So these are a couple of assumptions that we're going to make, but we're going to start with this. So if we need to set up our equation, we need to remember that Q of system is equal to negative Q of surrounding. Okay? Now, Q of system. System, in this situation, is representing the bonds that are formed or broken over the course of this chemical reaction. This is a change in potential energy. Potential energy, that's enthalpy. But when we measure enthalpy, we measure it in joules or kilojoules per mole. And remember, Q is just in joules or kilojoules. So we need to figure out, okay, we've got a delta H, we've got a Q. So we need to go ahead and use this assumption because in the end, the process here, we're looking for delta H of the reaction. So what I'm going to do is I'm going to start by saying, okay, if I need to find my delta H of the reaction, how can I get it from this setup? So let's take a look at that. So if Q of system and delta H of the system are connected, let's figure out how. Well, if delta H is kilojoules per mole and Q is just kilojoules, then it would stand to reason that delta H times the number of moles would represent my Q. And that's actually going to be the case. So what we're going to do is my Q of system, in this case, is going to be the delta H of the system times the number of moles. And my Q of the surroundings. Now the surroundings in this case is the solution as a whole. Be careful. Make sure that we're accounting for this solution as everything in the solution. This means the total mass of solution. Now, MC delta T, mass. 50 milliliters of 1 molar hydrochloric acid, 50 milliliters of 1 molar sodium hydroxide. Remember, one of the assumptions we make is that the density of any solution in water is that of water, 1 gram per milliliter. So if I've combined these two, I've got 100 total milliliters, which means I have 100 total grams. So my mass that I'm going to use here is 100 grams. The C that I'm going to use in this case, the C I'm using is going to be the specific heat of water, 4.84 joules per gram degree Celsius, and we're going to go ahead and use that. And again, that's another assumption we make. And unless given other information, it's a safe assumption. And finally, our delta T. Now we're given our change in temperature here goes from 21 up to 27.5 degrees Celsius. Now, the value here, whether we're using Kelvin or Celsius, doesn't actually matter because the difference between these two is the same either way. So our change in temperature is going to be 6.5 degrees. And that's a positive value in this case because the temperature went up. Now, the only thing we don't know yet, because again, we're looking for delta H, is moles. So moles of what? This goes back to our limiting reaction stoichiometry. This reaction is going to produce energy. But the amount of energy it's going to produce is the same as the idea as the amount of reactant used to produce a product. It's the reactants that are creating this energy as a whole, and therefore we have to attack it the same way we would have in a limiting reactant situation. Now in this case, we have the same initial number of moles of both sodium hydroxide and hydrochloric acid. So in this case, in this instance, neither one is going to limit, as it were. They're both, as it were, limiting because they react perfectly together. If there was a limiting reactant, we are only going to use the moles of the limiting reactant to determine our delta H of this reaction. Okay? But in this case, we're okay. But be careful. Whatever you do, do not add the moles together. It's a really common mistake that's made. So it's not that we're taking 1 molar 50 milliliter and adding 1 molar 50 milliliter, and therefore we double the number of moles. No. Moles of reaction. 1 of this, 1 of this, 1 of the reaction. So we're simply going to take the number of moles of either of these and plug it in here. So the final step, we need to just plug in values. So we've already plugged in for my MC delta T, number of moles. Remember, it's going to be 50 milliliters of 1 molar hydrochloric acid or of 1 molar sodium hydroxide because neither one is limiting. And if neither one is limiting, then we can use either one, but we're not going to add them together. So the number of moles is going to be 0.05 moles. All right, 0.05 moles. So we're going to solve for my delta H at this point. So 100 grams times 4.184 times 6.5, that multiplies together to give me 2,719.6 divided by 0.05, and that gives me 54,392 joules. If we want my delta H in kilojoules, then in kilojoules it's going to be 54.392. Be careful, remember that negative. So what we are going to end up with is, if you solve it out, a delta H of this reaction of negative 54.392 kilojoules per mole, and that's per mole of reaction, which in this case, because my coefficients are both 1, it's going to be kilojoules per mole of HCl and kilojoules per mole of sodium hydroxide. So in the end, this process that we've just accomplished, connecting our delta H to our Q value, the most critical thing to remember is keeping system and surrounding in line. Make sure you remember that the system is always a change in potential energy, all right, in this reaction calorimetry, and the surrounding is a change in kinetic energy in this reaction calorimetry. So you have to be able to connect your delta H to your Q. Remember, in each of these circumstances, in the end, your sign matters. Notice how our temperature of the surroundings went up. That means energy had to have left the system. Potential energy is leaving, which means that it's an exothermic process. That means my delta H needs to be negative. Just double check the sign at the very end of the problem to make sure it matches the concept and the context of your problem. So that wraps up today's video. Let's do a quick recap. We started by talking about how chemical reactions can be endo or exothermic and connecting it to reaction calorimetry. So remember, in reaction calorimetry, we're looking at how that change in kinetic energy of the surroundings, which we're measuring the temperature of, is related to the change in the potential energy of the system, where the reaction's happening. Remember, the reaction itself is the system. Those bonds and attractive forces that are forming and breaking, that produces the change in energy that is going to be seen as a change in kinetic energy of our surroundings. So remember, change of energy of system is all about potential energy. Change of energy of surroundings is all about kinetic energy. I'd like to thank Joe Ashelman and Kalani Turbak for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one. Something that is going to produce or take in chemical, or sorry, bad.